Sir Isaac Newton is considered to be the father of science. Indeed, all physicists think he is super cool, even me. Forget about Kanye West, forget about other people who I don't know. This is the man, Sir Isaac Newton. Today, let's have a look at his second law of motion. When the forces acting on an object are unbalanced, the object will accelerate. So let's unpack this statement a little bit. First, what does it mean for forces to be unbalanced? Well, we looked at last lesson, we need to consider all of the forces acting on an object. So here we have me in a SpaceX rocket accelerating upwards into space. So in this situation, I have my weight force, the pull of gravity downwards acting on me, but also the chair in the space rocket is pushing up on me. In this situation, if I'm accelerating upwards, well then the force acting up is going to be bigger than the weight force. They won't cancel out. So in this respect, we say the forces acting on Paul are unbalanced. Next, what does it mean to accelerate? Well, there's two ways we can accelerate. An acceleration could look like a change in speed, a slowing down or a speeding up, but it could also look like a change in direction. Last lesson, we saw that quite a few people thought that a satellite going around the Earth at constant speed must have balanced forces acting on it. However, with this idea of acceleration being a change in direction, well then a satellite travelling around the Earth at constant speed is clearly accelerating because the direction it is travelling in must continually change. So a satellite in orbit around the Earth is subject to an unbalanced force. Okay, so see how we can use this idea two ways. If the forces are unbalanced, then we can determine an object must be accelerating. Or we know that if an object is accelerating by changing speed or a change in direction, then the forces must be unbalanced. Now, Newton's second law of motion relates the unbalanced or net force acting on an object to the resulting acceleration that will occur. This is summed up in the formula F net equals mass times acceleration. So unpacking this equation a little bit, if we have an object with a constant mass, well then the larger the force, the net force that is applied to the object, the larger the acceleration of the object will be. Also, we could consider a constant force, so say 10 newtons. Well then, the higher the mass of the object, the lower the acceleration must be. So we know that from everyday life. If you push a small object with the same force as a car, well, the small object will accelerate at a much higher rate. Now let's look at a couple of example calculations using this formula F net equals mass times acceleration. In this first example, I see a 2 kilogram mass and it's being observed to be accelerating at 3 meters per second east. Okay, so I know mass and I know acceleration. That means if I substitute into this formula, I'll be able to calculate the net force acting on this mass. Doing so, we get 6 newtons east. So remember, to get the unit of newtons for force, we must be using kilos for mass and meters per second for acceleration. Also, force is a vector quantity, which means we need to put a direction on it. So in this first example, we see that if we know the mass and we observe the acceleration of the object or somehow measure it, then we can calculate the net force acting on the object. This doesn't mean we know what all the individual forces are on the object, just that they add up to the net force. In the second example, we see the same 2 kilogram mass, but here there's two forces being applied to it. One is 25 newtons right, the other 10 newtons left. So to use the formula, we need the net force. That means we need to add up the two forces acting on the mass. But how do we do that? There's two different ways. One, we could use a diagram to add two vectors together. We see I've done that down here. So I start by drawing the first vector, 25 newtons, and then I draw the next one from this end of the first vector, and that's 10 newtons to the left. You can think of this as adding two separate journeys on. One, 25 to the right, next 10 to the left. To get the net force, we draw the final vector from start to finish. So I see my answer here is 15 newtons to the right. I see it's 15 newtons because that's the gap here. I know it's to the right because going from start to finish is in that direction. Another way we can calculate the net force is by a calculation. So the net force is always the addition of all the individual forces acting on an object. Here we just have two, but in different scenarios we could have 3 or 4 or 5. Because they're vector quantities, I need to have a positive direction. So here I'm saying let right be positive. Then when I add in force 1, that's my plus 25 Newton force, plus because it's to the right. And then F2 was my 10 Newton force, and because that's acting to the left, it's negative. Now I can add these together and I get plus 15 newtons, but it's always a good idea to return to the actual direction in the question. So here the positive means to the right, so I have a net force of 15 newtons right. So now that I know net force and I know the mass, I can calculate the acceleration of the object. So rearranging, the acceleration is F net divided by m, which gives me 7.5 meters per second squared to the right, which is in the same direction as the net force. Now we need to have a chat about two physics terms, mass and weight. There's a real problem we face here because the term weight is used by non-physicists, which is a real problem because they use it incorrectly. Okay, so let's explore this idea of mass and weight, looking at my cat Nomi. So let's have a look at the different situations where we find my cat Nomi. Here Nomi is stationary, velocity is 0. As Nomi's velocity is 0, I know that his net force is 0, or the forces acting on Nomi is balanced. Here we have the velocity of cat to the right and the velocity of the kid to the right. Nomi's running away. Another scenario that occurred recently, we have the kid on the trampoline with the cat who is now having a velocity up and away from the trampoline. Another scenario, we have the cat who's been put into a pond, but of course the cat will return to the surface, and we see the velocity of Nomi is up, but he's underwater. Over here we have Nomi on the moon with the lunar lander and some aliens. Nomi's the first cat on the moon. Also, Catstronaut Nomi is in the International Space Station going around the Earth. Now, the International Space Station has an altitude of roughly 500 kilometres, or 400 to 500 kilometres. If you imagine the Earth as being a basketball, the relative scale of that is the International Space Station being just a few millimetres above the surface of the basketball. So on the scale of the Earth, the International Space Station is actually very close to the ground. It's not very far away in the scheme of things. So in all of these scenarios, Nomi is made of exactly the same things, which is mainly fancy feast, kibble, and pancakes from the bench on a Sunday. Now, what mass is to a physicist is really a measure of the amount of matter the cat Nomi is made from. So in each of these scenarios, it doesn't matter where Nomi is, what Nomi's doing, he is still made of the same matter. So in each of these scenarios, Nomi's mass is about 7 kilos. Nomi's a well-fed cat. Now in contrast, the term weight to a physicist is different. Weight is a force, and it's the force due to gravity acting on a mass. So what weight describes when Nomi is on Earth is the gravitational attraction Nomi has towards the Earth. So when Nomi is close to the Earth, the gravitational attraction he has doesn't change if he's running away from a kid, if he's underwater, if he's flying through the air, or if he's sitting still. His weight force, or the attraction Nomi has towards the Earth, is the same. However, when Nomi is on the Moon, his weight will decrease. That's because the mass of the Moon is much less than the mass of the Earth, so Nomi experiences less gravitational attraction towards the Moon than he would when he's on the Earth. So, on the Moon, Nomi's weight is less. When he's travelling around in the International Space Station, Nomi's weight is a little bit less because he's further away from the Earth. So the attraction Nomi experiences towards the Earth is reduced. Let's sum this up in the next slide. So going back to mass, the mass of the cat does not depend on where the cat is or what the cat's doing. It's a scalar quantity, it doesn't have a direction, and it's measured in kilos. We can think of it as a measure of how much matter, or fancy feast, the cat is made of. However, weight is different to a physicist. It is a force. That means it's measured in newtons and it has a direction. So it measures the gravitational force acting on an object due to all the nearby mass. So I say nearby because the universe is so big that masses on the other sides of the universe are so far apart they haven't been able to interact yet, even through gravity, which can travel at the speed of light. So that means the universe is so big that we can't see across it. Kind of cool. Now the really annoying thing about weight is that physicists call it lots of different things. So weight, weight force, force due to gravity, with the symbols W or Fg for force of gravity, or Fw for weight force, which is really annoying and very confusing early on, but something that we'll have to get used to. Now we need to look at how do we calculate the weight of an object, the force due to gravity. Now the weight force, or the weight of an object, is calculated simply by mass times g, the acceleration due to gravity. And we saw this in the recent prac, that the acceleration due to gravity was 9.81 meters per second squared. So that means if we drop an object and it's in free fall, and we don't worry about air resistance, it increases its velocity by 9.81 meters per second down each second. Now this is fine. I've put acceleration due to gravity in quotations here because this is clear or can work for an object that's falling. We see falling stuff accelerates all the time. However, for objects sitting on your desk right now, they still have a weight. They're still attracted to the Earth. However, they're not accelerating. So when we talk about the acceleration due to gravity, it is a little bit misleading. However, we'll fix that in year 12. Now, to calculate Nomi's weight, we use mg, which is 7 kilos times 9.81. So Nomi's weight is about 68.7 newtons down, or towards the centre of the Earth. So note here that the number is bigger than the mass, because we're timesing it by 9.81 in a very different unit. Now this value for the acceleration due to gravity does change depending on where you are. It does vary on Earth by very small amounts due to large mountain ranges. However, if you're in a plane or if you're running around or going up a hill or down in a valley, the acceleration due to gravity on Earth to three significant figures will be 9.81 meters per second squared. If you're in the International Space Station, 408 kilometers above the surface of the Earth, your acceleration due to gravity there will be 8.73 meters per second squared because you're further away from the mass of the Earth. On the Moon, the acceleration due to gravity is much less than Earth at 1.63 meters per second squared because the mass of the Moon is much less. So the force attracting objects towards the Moon when you're on its surface is much, much smaller. Neutron stars are pretty cool. The acceleration due to gravity on the surface of a neutron star is approximately this. We might look at that in astronomy. Now for an important part. Please stop playing this video really fast. If we want to predict how the motion of an object will change into the future, we must understand the forces acting on it. Freebody diagrams are how physicists do that. So here we've got an example. I've got my cat bungee jumping. Hopefully this isn't going too far. But again, mass 7 kilos. And at this particular instant in time, the cat is accelerating upwards at 3 meters per second squared. And the question here I've got is calculate the force applied to the cat by the bungee cord. So this is my free body diagram. So this box here is the way that a physicist would draw a cat or absolutely anything, just as a point mass. Next, we draw the forces acting on the cat, and we always draw them away from the center of mass. So the cat, because it has mass, will always have the force due to gravity or the weight force acting down towards the center of mass of the Earth. Also acting on the cat is the pull of the bungee cord up. Because the cat's accelerating up, I know that this force due to the bungee cord must be bigger than the weight force. So I've shown that in the free body diagram by making this vector longer than the weight force. Now to calculate the force of the bungee on Nomi, I write down the formula that the net force equals the sum of all the forces acting on my cat. The next line, I write the net force as mass times acceleration. Okay, so the net force is always calculated by the observed acceleration. The weight force is always mass times acceleration due to gravity. And here I'm trying to figure out the bungee force. Now we always need a positive direction when we're working with vectors. So here I'll let up be positive. So substituting in, the mass of Nomi is 7 kilos. The acceleration is 3 meters per second squared up, so it's positive. In contrast, to figure out the weight force, the acceleration due to gravity is negative because it's acting down. Simplifying these, I get 21 equals minus 68.7 plus F bungee. And solving here for the bungee force, I get the bungee force is 89.7 newtons up. Okay, thanks for watching to the end of the second forces video. That last example was definitely more challenging than what you'll be expected to do initially, but just the main ideas there are really important. Perhaps watching it a second time would be good. I'm going to reinforce your understanding now on style. And that's the short activity that will really help consolidate these ideas, which are very important for Year 11 and essential for Year 12.